Everyone. We are live. Assalamu alaikum, everyone. Welcome to the fifth conference in AI Summit 2026. I'm your host, Ayabna Lekhuja, a technical manager at School of AI. Today, we're covering one of the most interesting topics and fully independent research direction led and driven by Yann LeCun, which is about the joint embedding predictive architectures. The speaker for today is Imane Hamzaoui, one of the brilliant alumni of School of AI, who is a candidate, PhD candidate in Quebec, Mila, specialized in Euro AI. Welcome among us, Imane. A pleasure to have you as always. Please go ahead. The stage is yours.
Wa alaikum salam. Thank you, School of AI, for the invitation. And thank you for the nice introduction. Today, inshallah, we're going to talk about self-supervised learning and JEPA architectures. I noticed that there has been an interest about this topic by some Algerian researchers, so I wanted to make a small presentation about it. I hope it's not too technical and it's understandable. Okay, so let's start. I think most of us know about self-supervised learning and the advancements that we have, but when we say supervised learning, we're talking about money. Which money exactly? The money needed to label datasets. As you know, ImageNet took around 25,000 person-hours to label, and medical imaging, for example, requires expert radiologists. And models don't generalize well outside training distribution. And in nature, humans learn from observation, not explicit labels. And language models already exploit unlabeled text while vision lags behind. So we'll try to focus a bit today on vision tasks, so self-supervised learning for vision. As you can see here in this graphic from GDS Online, where we have an estimation about the cost of labeling datasets for different types of modalities. And you can see, for example, for semantic segmentations, it can cost more than $1 million to annotate million samples. And that's where self-supervised learning comes into play. So what is self-supervised learning? In self-supervised learning, unlike unsupervised learning, where we don't have supervision at all, the supervision comes from the data itself. We train a model to predict part of its input from another part, and the labels come free from the data structure itself. So in this...
Sorry for the interruption, Imane. Can you please reshare the screen?
Okay.
Yeah, suddenly they lost it. They can see
it. Where did you lose the...
I guess when you... Okay. Yeah, this one.
Okay. So I was talking about the price of the supervision and how much it costs for certain modalities. It can go further than $1 million. And that's where self-supervised learning comes into play, where we don't have labels, unlike unsupervised learning. The supervision comes from the data itself. We train a model to predict part of its input from another part. And the labels come free from the data structure itself. And in a self-supervised learning pipeline, usually in most algorithms that we know so far, we have a pipeline that looks more or less like this. We have an unlabeled source data set. That's the one we're going to train on. And the label target data set is just for evaluation and testing. So for the unlabeled data set, we're going to do what we call the pseudo-label generation process. We're going to generate this Z, which is usually considered as the hidden representation. And we have a self-supervised pre-training phase where we're going to predict hidden latents, and we're going to calculate the loss according between these representations. Usually it's representations, but we're going to call it pseudo-label to be more general. And for the label target dataset, we're just going to evaluate how our model is good, or so we call it the downstream task adaptation, because here the loss is not really telling about how good we are. So we need some sort of task to evaluate on at the end. And yeah, it can be a linear probe or classification or anything. And in some cases, we can even fine-tune the model that was trained in a self-supervised way. So what do I mean by a pseudo-label generation process? What do we have in this phase? So we have many ways to do it. Let's say we have an image, a picture of a dog, and we can do a transformation prediction by trying to predict the transformation. So here we have the image of the dog that is rotated. It can be cropped. It can be color jittered, etc. Any transformation we can apply to this data. We have the masked prediction, like we have in masked autoencoders. So we mask a part of the image and we train on, we try to predict it later. And we do have instance discrimination. Here, for example, we have a picture of a dog, a picture of a cat, and a picture of a dog. So which one is the odd one? The cat is the odd one, and we need to discriminate that, okay, image 2 is not part of this class. And we do have clustering. So if we have different types of data, like images, for example, here, and this one is a transformation of this one is a transformation of this one with a different filter, etc. And we're gonna try to cluster these images together. So ideally, I will not have a cat here. The white dog is gonna be here. This type of dog is gonna be here, and the two images of a cat are gonna be here. But we have some error that we have this class that's here. Anyways, it's just clustering. And we do have a contrastive instance discrimination. And what do we mean by that? So if we have these three images of these two images are similar, and this one with this one are not similar. So we're gonna train our model to pull these ones together. So the weights between these two are gonna be put close together in the representation space, if we're talking about representations, and these two are going to be pushed apart since they do not talk about the same entity. We have a dog and the cat, so they need to be pushed apart. So there are different types of self-supervised learning algorithms or ways to do it.
Sorry, Imane.
Yes.
Again, we lost the slides. Can you please reshare?
Okay.
Thank you.
Let me know on which slide did I stop.
I guess you stopped the one where we were tackling the pseudo generation process. Yeah, this one.
Okay. Do I need to explain this one or the one after?
You've talked about, I guess. Yeah, start from the beginning.
Okay. So we have information prediction where we have an image and a rotated image or a differently colored image. We're just going to apply some sort of transformation like color jittering, different angle, different filter to the image, and we're going to try to learn that. We have mask prediction like we have in mask autoencoders, where we're going to apply a mask on this section and we're going to try to predict it. We have instance discrimination. So which one is the odd one? Two, for example, is a cat and these two are dogs. So the odd one out is number 2. And for clustering, we have different different images here, and they consist of the same entity but with a different rotation, different color, jittering, etc. And we're gonna cluster them and try to put the similar ones together. So this one is class 1, this one is cluster number 2, and this one is cluster number 3. And here we have some error because this dog should belong here. But of course we're gonna have some error. And we have contrastive instance discrimination. And this one has been used by, I think, SimCLR and I believe maybe Moco. So we try to pull the similar ones together and push apart the ones that are not similar, like separate them and push them apart. So here we would have a weight 1 for this connection here and a weight 0 for this connection here. So this is about the pseudo label generation here, process that we have here. And we do have many types of self-supervised learning algorithms. We have earlier works that use pretext tasks, like trying to predict rotation, color, context, and it has been hand designed. We have contrastive ones. We try to pull similar views together and push the negatives apart like SimCLR. And we have the generative approach, which is trying to reconstruct masked patches like mask autoencoders, BIT, which is the image version of BERT, and we have IGPT, which is the image GPT. And of course, we have JEPA that falls into a fourth category, which is predictive in the representation space and not the pixel space like the mask autoencoder one. And so it all started from pretext tasks, as I mentioned earlier, and we have modern representation learning as we know it today. The earliest works for self-supervised learning, I can mention Word2Vec, which is the SSL for NLP. We have GPT BERT and mask language models that appeared in 2018. 2020, we have seen SimCLR, Moco V2, and there is a version 3 that appeared later. 2021, we have known BEOL, Dino, mask encoders, BIT, which is like the image BERT. And 2022, the IJEPA paper has been introduced with Dino V2. And lately we have known video JEPA, audio JEPA, and many, many more papers that have appeared very recently with the JEPA architecture. So let's start with SimCLR and the Moco models. So some key concepts about these methods is that they rely on augmentations. We can apply a random crop or a color jitter or blurring of the same image, and they would consist a positive pair. So for example, these two images here, we're gonna attract them together. These two as well, we're gonna attract them together, but this one with this one, we're gonna repel them because they don't consist of the same thing. Here we have a chair and here we have a dog. Moco uses a slowly updated copy to avoid representation collapse by using momentum encoder. And BEOL uses a prediction head plus a stop gradient, so no negative samples are needed. And
Sorry, Imane.
Yes, again?
Yes, sorry.
Okay. I don't know what's the issue. I don't have anything open. Okay, I think I'm on this slide, right?
Yes,
Or
yes.
should I go before? Okay. Okay, let's look at the example here. We have this image of a dog and a different angle of the dog, and we have two images of a chair. So there is some sort of augmentation that have been applied to both. And then what we're going to do is that we're going to try to attract these two together because they consist of the same entity. Same for these two. They are both of them are images of a chair. And we're going to try to pull these ones apart, try to repel them from each other because they don't consist of the same thing. This figure has been taken from the SimCLR paper, and Moco came after it, and it uses a momentum encoder. It means it uses a slowly updated copy to avoid the representation collapse. And we have the BEOL paper that uses a prediction head plus stop gradient, and no negative examples are needed. So researchers thought that, oh, okay, this might not work, but surprisingly, it has worked. No negatives were needed. And we have the representation collapse problem. So without negatives or asymmetry, there is a risk that the encoder outputs a constant vector and it doesn't learn anything. Another famous SSL architecture is the masked autoencoder, also known as MAE, where we're going to mask 75% of the picture. We're just going to leave 25% of the patches, which makes it fast plus efficient at scale. We pass them through an encoder. We have latent representations, and then we have a decoder that would try basically to predict the masked parts of the image. So we have a 75% masking ratio, which counterintuitively higher masking means better representations, and it prevents shortcut learning, because one would think that if you mask less, you would learn better, but actually the more you mask, the more you learn better. And on ImageNet, it achieves 83% accuracy, and it's a very competitive result with supervised vision transformer base. The limitation of this method is that it predicts in pixel space and very computationally heavy, and it might learn textures over semantics. And in 2022, there has been the famous Jan Lequin's paper. I think it's a white paper, if I'm not mistaken, or a position paper, and that has introduced JEPA. The idea behind it is to predict in the representation space and not the pixel space, and to discard irrelevant details and keep the semantic structure, which was the issue with the masked autoencoder. So why not the pixel space? The pixel generation is computationally expensive, and most pixel information is irrelevant to understanding, and it is very hard to scale to video and 3D data, and the energy most of the times is spread over irrelevant details in the image, in the model. While JEPA has many advantages, it predicts abstract latent representations, and it avoids representation collapse via stop gradient mechanism plus the exponential moving average target. And there are no negative samples that are required, and it scales pretty well to video and audio and multimodal data. So we have the iJEPA paper, which is the image JEPA architecture, as you can see here. So we would start with a context patch. We're going to encode, so we're going to try to divide the image into non-overlapping patches. We're going to encode them, and we have another other target blocks, let's say 4 per image with like 40% coverage. And
Sorry, Iman.
yes.
Please, this time, I guess the problem arises from when you open the slides in the wider view. So if you can avoid this.
Okay, so I should wait. So I would just leave my screen visible, right? Like this.
Yeah.
Okay, just try
Slideshow.
to zoom in maybe. I hope it's visible.
Yeah, it is.
Okay, we will not have animations, but it's okay. We don't have many from the first place. Okay, so as I said, we would have to divide the image into non-overlapping patches and pass them to a context encoder, and we would have target patches which can be overlapping, and we're gonna pass them through a target encoder. And while learning this, we're gonna mask actually, for example, here, this blue square, we're gonna mask that part of the image. Here, this red square is actually overlapping with this section over here, so we're gonna mask it. Same for the yellow one. Here we don't have overlapping, but it's okay. And we're gonna have a predictor network, and we're gonna try to calculate the loss between these two. So we're going to predict VIT representations of target blocks from context, and there is no data augmentation that is needed, and the semantics emerge naturally. The same thing for videos. The same principle of iJEPA is used with VJEPA, and the how do we scale to video is, have you seen the mask that we have applied here? It was only to a part of the image. For the video, since we have a sequence over time, then we're gonna mask those the same patch over sequences. So there is no pixel decoding. All the prediction happens in the VIT token space, and it's 4 times faster than video Imane, which is like very computationally expensive. And we do have, with this type of architecture, the action understanding. So unlike static image SSL, that must understand motion, causality, and object dynamics. And we have these spatial temporal tubes, this idea of masking that we have. We mask entire temporal tubes across the same spatial location across T-frames, and it forces the model to learn about motion. And we have a frozen encoder fine-tuning, so with a frozen backbone plus linear head. So we take the VJEPA model that Meta has produced, and oh, there's an error here, but it's like the VJEPA paper. With the frozen backbone, plus we just add the linear head just to do the prediction on a task that we want. It achieves state-of-the-art on the dataset K400 SSV2, which is a kinematics dataset. So what's the difference between iJEPA and masked autoencoders? We're gonna put this all into one slide. So masked autoencoders predict masked pixel values, while iJEPA predicts masked patch embeddings. So it happens in the embedding space, in the representation space. We do have a heavy decoder architecture based on transformers, and the JEPA has lightweight prediction head. The reconstruction happens in the pixel space, while the prediction in the abstract space. And we need high compute for reconstruction, and for iJEPA we have a more efficient training signal, and it is very MAE is sensitive to low-level textures, while iJEPA captures semantic structure, and the iJEPA beats MAEs in accuracy on ImageNet. Okay, and after the appearance of these papers, there have been many other ones that have appeared. Like we have now audio JEPA, we have multimodal JEPA. So the audio JEPA operates on mel spectrogram patches over 2D time frequency, and it uses it masks temporal blocks of the spectrogram, which means it predicts the representation just like before, and it outperforms the generative audio SSL baselines. And we have other multimodal JEPA architectures. So we have the image JEPA, video JEPA, audio JEPA, maybe a language model JEPA, etc. So we have here a little figure that compares different most famous and self-supervised learning methods from SimCLR that is contrastive, and the target space is SimCLR, BEOL, and Dino. All of them are in the embedding space, and I think the share screen has been disconnected. Okay, the host has been disconnected. We're gonna wait for them to come back. Okay, I hope you can see my slides. We have, okay, I was talking about how they predict in the embedding space, and Mascatoy encoders are generative. IJEPA and VJEPA, both of them are predictive, and the target space is the abstract representation space. And most of them don't need negative examples, and each one of them is suitable for certain types of tasks. So one of the things about self-supervised learning, especially the latest papers that have came out, is how to evaluate them. The loss is not very telling about their performance. So we have many evaluation protocols. We can use a linear probe, which means that we freeze the encoder. For example, if I have downloaded IJEPA or VJEPA from Hugging Face, I'm gonna use it just as it is, and then just train a last layer towards the end. Simple one to do a certain task, which tests the representation quality directly. We have semi-supervised. So we can, if our target task is, let's say I have IJEPA and I want to use it for a context of medical, a medical task, then I'm gonna use, gonna fine tune with 1 or 10% of the labeled data to test data efficiency. And we have the KNN, K nearest neighbor evaluation. So no training needed, nearest neighbor in the embedding space, and we get a clean 0-shot test. And we have transfer learning, which is to fine tune our CFAR, Oxford Flower, iNaturalist, and it tests generalization. So these are some highlights from the IJEPA paper, and it outperforms a lot of the baselines that we have, and I think that's the reason behind this growing interest in this architecture. So we do have some limitations and open questions. We have the most riskiest thing is that we have the representation collapse. So despite using the exponential movement average plus the stop gradient, collapse can occur at extreme learning rates or with small batches. So careful tuning is required. And we have mask design sensitivity. So the choice of a target block size and count significantly impacts the quality and still requires hyperparameter search per domain. Scaling to language. So can JEPA architectures replace causal language models? Predicting in the embedding space for text is non-trivial, and it's still an open research question. We have an evaluation overhead. So linear probing requires training ahead, not truly 0-shot, and full fine-tuning often is needed for competitive results. And we don't have discrete tokenization yet. So unlike the BIT, IJEPA targets continuous reps, and future work might discretize for hierarchical learning. And we have a limitation about interpretability. So the learned representations are hard to visualize or interpret. So what exactly the predictor encode? So for future directions, What's next for JEPA and SSL? So we have hierarchical JEPA, and this has been mentioned in the white paper by famous 2022 paper by Jan Lequin. So multiple levels of abstraction and low-level patches predicts low-level patches predict to mid-level objects, which predict to scene-level concepts and to mirror the visual cortex hierarchy. There has been also interesting talk about JEPA plus reinforcement learning. So the use of JEPA word model for model-based. Oh, it has disconnected again. Give me a second. Okay, you still can't see the slides. Okay, they're back. So there is also I was talking about JEPA plus reinforcement learning. So how to plan in abstract latent space, and there is a potential for sample efficient agents. There is also talk about multimodal unification. So a single JEPA encoder for image, audio, text, video, and a cost model prediction task align representations across modality without contrastive pairs. This would be very interesting. And we have 3 dimensions and embodied AI to extend to 3D point clouds and robot observations to predict future robot state representations from current observations and planned actions. So I'm currently working around this, like the JEPA plus action conditioning. So yeah, I think we came to the end of my presentation. Thank you for listening. I'm ready to receive any questions if you have.
Thank you so much, Iman, for the great presentation. We'll be waiting for any questions to pop up. Okay, so we've got the first question. She said, "Hi, Iman. Thank you for the presentation. How would you explain the technical building blocks of JEPA in a simple way?"
Okay, so do you want the JEPA or the iJEPA paper? Like the JEPA abstractly, like in the Unlocas paper, or is the architecture that I mentioned in this slide? Okay, the normal JEPA. I might have to show this slide.
Okay.
Okay.
Yeah. She says normal JEPA.
Okay. For a normal JEPA, the core idea is instead of trying to predict a pixel, like I start with an image, for example, and then I try to predict the output with a modality, or if I start with a video and try to predict a video, we're not going to do that. We're going to embed them. We're going to go to the representation space because similar things are going to be represented together, right? So they're going to be put together in the representation space, and we're going to compare them. We're going to compare the predicted latent with the ground truth latent. So that's the main idea between the JEPA. It's because in the pixel space or any like any data modality that we're going to use, the idea is not it's just to stay with the latent and the hidden space. I hope it's a bit clear. And we don't need any negative samples. I don't need to tell someone this is a cat and this is a dog. Oh, this dog is not a cat. You're just going to teach him what is a cat, and they're going to have this idea in their world model.
Okay, another question. Obviously from Wa'il. How can JEPA be integrated into reinforcement learning without being destabilized by the non-stationarity of state action distributions induced by a moving policy. I wish you can share any insight.
I actually don't know how we're gonna avoid this destabilization. Personally, working on action conditioning, so we do have actions that are gonna change the environment, but there is also a risk of representation collapse.
Yeah.
So there is still work that needs to be done uh, on how to solve this issue. It's an open research problem. We still haven't seen many papers within this realm. There is one paper from our lab that's called SIG JEPA, but I'm not very familiar with reinforcement learning plus JEPA literature. I don't even know if it has been tackled or no. I've never heard about it for the moment. It's just an idea. I've heard a lot of discussions about it, but there are a lot of challenges to solve this question. I mean, one of you should do that.
Yeah. Inshallah. Why not? Other questions?
And I apologize for the slides. I don't know what's the issue.
No, no worries. So another question. What are your actual use cases with JEPA, sorry? And thanks for so much for your answers. So she is asking about the use cases of JEPA.
So I think it can be used everywhere. So anywhere where we have used mask encoders, where we have uh, everything where we had, I think SSL so far, we can use JEPA for it. But I think it's very suitable for action conditioning. I have personally used also a video JEPA because it's very, compared to the video models that we have seen before, like stable diffusion, stable video diffusion and other models. VJEPA, for example, is rich with motion and uh, like 3D information, sorry. So personally, I'm working on neuroscience plus SSL, and that's my use case for the moment. And we use these JEPA architectures as a world model of the brain or for the visual cortex. So we use it to model certain. In the past, people used to use simple other architectures, other neural networks, but for now we're using JEPA models or word models. So I see there is a question how iJEPA compares to VIT in terms of inference time. I actually didn't do this calculation, but it should be faster than the VIT because we don't have the heavy transformer. I don't have a number in mind, but I know that JEPA is much faster than other architectures for inference. Yeah, I've seen the Low World model paper, but I didn't understand certain things. Maybe because it was, if I'm not mistaken, it's from the Meta Paris team. And if I'm not mistaken, I remember seeing the le, and I feel like they have translated sentences from French to English, and there were I didn't understand it pretty well, but the result of the paper is quite good. So, but it was not very understandable to me. Um, okay, there is a question. Thank you. There's a question that says, "Thank you for the presentation, and please can you explain aleatoric uncertainty, how it is related with iJEPA?" I don't know what is aleatoric uncertainty. Can you please explain what do you mean by that? Okay, let me just Google it. Okay, refers to the inherent randomness in data or outcomes. I personally don't have a response to this aleatoric uncertainty. It's not something that I have looked up before, but I will definitely look it up and provide an answer. So please send me an email or contact me. If you don't have my email, let me know.
It's okay. We can provide him with your email.
Okay, that would be good. Thank
Okay,
you.
I guess.
I'm quite curious about like are like a lot of people working on like these or using these types of architectures at maybe ESI or UNSCA? Because I've seen a lot of people talking about them, so I'm just curious.
Yeah, there is a question also from Imane. He's saying, why is applying JEPA to text still challenging?
We don't have a discrete tokenization. So I think also the causality, we don't have this notion of causality in JEPA, while in recent language
Yeah.
model we do have like this aspect. Oh, okay. Now I understand your question better about the aleatoric uncertainty. Yeah, generative models definitely predict they have a lot of noise. I have personally started my project using generative models, and they were not working. There were a lot of noise. There was no consistency. There is a consistency issue. I mean, because of the architecture, about the generative nature of their generative nature, but the JEP, JEPA architecture or the JEPA models are like word models. They are not just I don't know how to say this, but it's the whole idea behind word models.
So we can say that it's somehow robust to predicting that noise.
It's not the question of robust or not, but they are completely different approaches. So approaches the way they are the models are trained have noise, and then we keep adding noise, and then we generate stuff. First of all, we're doing it in the pixel space. For example, for videos we don't have consistency, but JEPA they're completely different approaches. It's not even approaches, they are different concepts.
Yeah,
So
different philosophy. Yeah, totally understand.
yeah, exactly.
Okay, any other questions? I guess there are no more questions. And we can wrap up the talk here, unfortunately. Thank you so much, Iman, for the
Thank
great
you,
technical
Mary.
details. A pleasure to have you as always. I wish to see you in our future events, inshallah. Thank you a lot. Thanks everyone for attending the talk. See you in the next conference, inshallah.
Thank you so much, and thank you all.
Thank you.